A test charge of positive 2 microcoulomb is placed halfway between positive 4 microcoulomb and positive 6 microcoulomb charges separated by 10 centimeters. Okay, so we are given a test charge. Let's call it Q0. Positive 2 microcoulomb. And is placed between two charges, Q1, which is positive 4 microcoulomb, and Q2 is again positive, and it has 6 microcoulomb charge. And the distance between Q1 and Q2 is 10 centimeters. Let's call it R1, 2. Now, the test charge is placed between the two, halfway between the two, meaning the distance between 1 and 0, that's the unit, the test charge, is equal to 5 centimeters. In meters, that will be 0.5 meters. Okay, and the same thing, R2, the opposite direction, and the same distance, that's going to be 0.05 meters. Now, if we sketch the charges, that's going to be something, if you have like a test charge right here, which is Q0, it's placed between two charges. Let's call the one to the right Q2, one to the left Q1. It's arbitrary, you can exchange this. R1, 0. And what we are asked to find in A is what is the magnitude of the force on the test charge, so F naught on the test charge. F naught on 0. To do that, now we need to find the force exerted by each charge on the test charge. Now, to calculate the electrostatic force between charge, we need a constant called electrostatic constant, and that is K sub E, and that's equal to 9 times 10 to the 9 Newton meter squared per coulomb squared. Alright, so what is the force exerted by charge Q1 on our target charge, which is a test charge Q0? Let's call it F1, force exerted by 1 on the unit charge, or the test charge. That will be equal to the electrostatic constant multiplied by Q1 times Q0 divided by the square of the distance between the target charge and Q1. That is R10 squared. Let's plug in the numbers. Force exerted by 1 on the target charge is going to be 9 times 10 to the 9 Newton meter squared per coulomb squared multiplied by the charge on 1, that's 4 microcoulomb, that's 4 times 10 to the minus 6, micro stands for 10 to the minus 6 coulomb, and that is multiplied by 2 microcoulomb, 2 times 10 to the minus 6 coulomb. Divide that by the square of the distance, that's 0.05 meter squared. So the force exerted by 1 on 0 is equal to 28.8 newtons. And what's the direction? Q1 is positive and our target charge is positive, therefore the force that exists between the two is going to be repelling force. So Q1 is going to repel Q0 to the right. So the force is to the right. What about that of the force exerted by Q2 on the target charge. That's going to be, let's call it F2 0. That's equal to electrostatic constant Q2 times Q1, Q0 over R2 0 squared. Alright, so F2 0, plugging in the numbers, 9 times 10 to the 9 Newton meter squared per coulomb squared, multiplied by the charge on Q2, which is 6 microcoulomb, 6 times 10 to the minus 6 coulomb, multiplied by the charge on the test charge, which is 2 microcoulomb, 2 times 10 to the minus 6 coulomb. Divide that by the distance between charge 2 and the target charge, which is 0.05 meters squared. That's equal to 43.2 newtons to the left. Again, because Qt is positive, positive repels positive, therefore this is going to be force exerted by Q2 on Q0 to the left. Alright, so what is the net force going to be? F net on the test charge is going to be the difference between the two. So if we take R, the right one, which is F10 minus F20, conventionally left is negative and right is positive, therefore this is going to be 28.8 Newton minus 43.2 newtons. Alright, so if it takes the absolute value, it will be positive. I mean, the magnitude will be positive, but the difference is going to be negative 14.4 newtons. So therefore, the magnitude is going to be 14.4 newtons, and the direction, B is asking for the direction. Okay, so it's to the left. So the magnitude is 14.4 newtons, and the direction is away from Q2. Alright, so 14.4 newtons to the left will be the net force exerted on the test charge.